Record. So good news. Nobody needs to remind me today. Oh, I'm so sorry for that yesterday, especially that table. I wanted it recorded. Ah, okay. We are recording. I have enough people here for me to want to have class. So I am going to set up my screen so I can share it. Let me actually do one more thing before I'm back. If you weren't here, it's like I was never gone. All right. Welcome, Hazel, Christina, and Raul. I appreciate you being here. Let's get to this. I'm going to share my screen. Let's do some calculus. I wish one more person would show up and then I wouldn't have to see myself. I'm going to stop my video because you don't need to watch me think. It's weird. Okay. Screen sharing, still recording. Okay, here we go. Inverse trig functions derivatives. So we're looking at, remember chapter 5 is all the extra stuff. These are actually called transcendental functions. The logarithm, the exponential function, the inverse trig functions. So we're getting a look at some of the somewhat common but odd math functions out there, and we can still find derivatives. So here we go. Definitions of inverse trig functions. First of all, keep in mind the inverse is only defined on a specific domain. So arc sine, y equals arc sine of x if and only if sine of y equals x, right? So it's the whole inverse idea. And sometimes we write this as y equals sine inverse of x. In calculus, we'll almost always use the arc sine because this -1 can, you write a little sloppy, it can easily be misunderstood. So we'll use arc sines almost exclusively. They have specific domains, right? Because the sine has a range from -1 to 1. The arc sine or the inverse sine has a domain from -1 to 1. Same with cosine. Right? The range of tangent and cotangent is all real numbers. So the domain of the arc tangent is all real numbers and so forth. Notice here, the arc sine is only defined in quadrants 1 and 4. Negative pi over 2 to 0 to pi over 2. Inverse cosine is only defined in quadrants 1 and 2. Over here it's positive, and if it's negative, we're on the other side, and so on. And they kind of all correspond in one way or another. And really, when it comes to finding the derivatives, we have to memorize these formulas. Right? And there is I'll send you a link to it, or I'll just send you the page. There's a sheet that has all of these formulas. It's a sheet that we give you for the exam 3, and I will make sure you all have a copy of it before the exam rolls around. Actually, I need to send it to you soon so that we can have it for the quizzes as well. But check this out, right? The derivative of the arc sine of u. The derivative of u divided by the square root of 1 minus u squared. Derivative of the arc tangent. Derivative of u in the numerator, and the denominator 1 plus u squared. Arc secant in the numerator, derivative of u, right? So derivative of the inside. And in the denominator, the absolute value times the square root, and a parenthesis is missing. Oh, guess what? I could type that in because that's actually typed. So all of these are pretty straightforward, right? And they're different. One is different from the other in that arc sine and arc secant both have a square root, but the order is different, right? 1 minus u squared for sine, u squared minus 1 for secant. So there's these slight differences, and the secant has an absolute value in it. Arctangent doesn't have a square root, and it's the only one with positive. But look what we have on the other side. Arc sine and arc cosine, the only difference is this negative sign. The only difference between arccotangent and arctangent is the negative sign. So if you memorize these are just the negatives. So arc cosine, arc cotangent, arc cosecant. Just the negatives for the cofunctions. So you only have to memorize 3 and you're ready to go. And so let's do that. We're going to do a little bit of work first. There are 5 problems that are just trigonometry working with inverse trig functions. And some of you are really good at this and did awesome in this section in pre-cal, and some of you were really glad that algebra came first in pre-cal because you still made it by with, oh look, I'm not on video anymore. You still made it by with 1, 2, 3, damn, I'm not. I talk with my hands, you need to see me. Y'all, it's been a rough day. Let's do this problem. There we go. Evaluate without a calculator. There's no calculus whatsoever. Our hint is make a sketch of a right triangle, but I'm going to do this problem a little bit differently. I'm going to do these 2 problems differently. So let's look at A. I'm going to let U be the arc cosine, 2 C's, arc cosine of the square root of 2 over 2. Then the cosine of U, right, if we take the cosine of both sides, is square root of 2 over 2. So we know that U must be pi over 4 because you all know your unit circles. And because you know your unit circle, cosine and sine are both square root of 2 over 2 at pi over 4, we know this U value is pi over 4. But if I make this entire thing U, I then have that the tangent of U, which is the tangent of pi over 4, is 1. So no triangle needed. But that doesn't make this a bad hint. Because when we look at part B, I'm looking at let U be the arc sine of 5/13. Then the sine of U is 5/13. And I don't know an angle, like a 30, 45, 60, 90, whatever, that gives me 5/13. And this is where the hint is actually helpful. Because we're using the arc sine, we know that arc sine must be in quadrants 1 or 4. Why I mentioned it up here, it's almost like I have forethought, right? Quadrants 1 or 4. But since the 5/13 is positive, it must be in quadrant 1. So I'm going to draw a standard quadrant 1 angle. Let me call it U. The sine is opposite over hypotenuse. And we can find our missing side. I'm going to call it X. Because X squared plus 5 squared equals 13 squared. X squared equals 169 minus 25. And because we're in the first quadrant, we know this X is a positive 12. What we have here, this whole thing is U. We know that the cosine of U, there's U, cosine is 12 over 13. So it depends on what the inside looks like. If it's a nice square root of 3 over 2 or a 1/2 or a 1 or a 0 or a square root of 2 over 2, a nice little unit circle number, you could do it like we did part A. But if it's not a nice unit circle type number, then we sketch a triangle to help us look at this. And I think this tip is going to help you on 3 different problems, 3 out of the 5. So go through those. If you need to, check out my pre-cal lecture on inverse trig functions. You don't have to be an expert on them. We're going to work on them now. Find the derivative of the function. All right, so derivatives. Now, I am going to okay, I see arctangent. So the first thing I do is the first thing I do, honestly, is I scroll back up and I look at the formula. As soon as I see arctangent, I need this formula. U prime over 1 plus u squared. All right, so that's my formula. But I also see here a multiplication. So I know I'm going to have a product rule. And we could go old school. I want to use u. I'm not going to go old school. I'm just going to write it out. So we have first times the derivative of the second. All right, in this case, my u is 6x. So the derivative of the arctangent of 6x will be the derivative of 6x divided by 1 plus 6x all squared, right? Just wherever the u was, that's 6x. Derivative of u, derivative of 6x. 1 plus u squared, 1 plus 6x squared. And I simplified that 6x all squared into 36x squared. First derivative of the second plus second times the derivative of the first. The only thing I would really do to tighten this up before I typed it in is I might call it 6x squared over 1 plus 36x squared. And then I'm going to move that 2x to the front so it doesn't accidentally slide inside that arctangent. But this would be my answer. And let's see what's on the screen. Oh, good, good, good. You can see there's even the right answer. I even put in number 3. So yeah, I'm doing these problems ahead of time. It works out so much better. It looks like we should probably do number 7. Let me hit save, even though it says it's saving. All right, number 7. Find an equation of the tangent line. So I know I'm looking at y minus y1 is the derivative times x minus x1 at the given point. All right, we can do that. So first of all, the derivative of 3 arc sine, I go back to my notes. I look at my formula sheet. And the derivative of arc sine of u is u primed over the square root of 1 minus u squared. Oh, I got it right. I always have to check. I don't always have it memorized either. But I'm working on it. So my derivative, we're going to leave the 3 alone. The derivative of arc sine is, so I take the derivative of the inside. It's just an x though, so that's no problem. The derivative of x is 1 over the square root of 1 minus x squared. That's not so bad. We can do that. So this is our m value if we substitute 1/2. So our slope is the derivative evaluated at 1/2, which is 3 divided by 1 minus 1/2 squared. 1/2 squared is 1/4. And 1 minus 1/4 is 3/4. So let me write it as 3/4 and then square root of 3 over 2. Right? Because the square root of 3/4, that's the square root of 3 divided by the square root of 4. Square root of 3 and square root of 4 is 2. Dividing by a fraction, I can instead multiply by the reciprocal. And this looks like 7 over square root of 3. However, I claim that it is not. If we multiply to rationalize our denominator, we'll get 6 square root of 3 over 3, which is 2 square root of 3. It turns out that square root of 3, 3 divided by square root of 3 is just square root of 3. So you could go from this step here to the answer if you understand that whole division by the square root of it itself. If you don't, these steps always work. But remember, I'm looking for the tangent line, not just the slope. So I know my slope. Let's put in our line, y minus y1 equals m times x minus x1. I'll get y minus pi over 2 equals 2 square root of 3 times x. Make sure that square root ends before the x comes down. Minus 2 somethings times a half will be just that something. And when I write it in here, 2 square root of 3x minus square root of 3, I'm just going to write it as plus pi over 2. That's exactly how I'm going to write it. Maybe I'll write it bigger over here so you can all actually see it. And the y equals is on the outside. So really, what did we do? We did calculus and algebra. The calculus in these sections is really straightforward because it's just formula driven. For natural log, right? The derivative of a natural log is derivative of the inside divided by the inside. For an exponential function, e to the x, derivative is e to the x, the antiderivative is e to the x. It's itself. It's the greatest function ever. And you'll find out more why that is in Cal 2, and hopefully it blows your mind when you see it. And if it does, email me or step by my office. Like, you're right, Tuesday, e to the x is pretty awesome. All of these, they're just a formula. So we'll have a formula sheet. You just need to know how to manipulate them. So we're just practicing our trig and our algebra all over again with new formulas. All right. So we did one that was just find a derivative. We did an equation of a tangent line. Let's look at relative extrema of the function. So when I'm looking at relative extrema, I'm of course looking for maximums and minimums. So in order to do that, my critical numbers are where the derivative is 0 or the derivative does not exist. All right, let's give it a shot. First, the arctangents here. So my rule is derivative of the inside divided by 1 plus u squared. Each individually, f prime of x, the derivative of arctangent of x, right? When it's just an x, the derivative of x is 1 plus x squared, not bad, minus the derivative of arctangent has this format. Remember, our u is x minus 9. The derivative of x minus 9 is still 1 plus x minus 9 all squared. Now, when I'm looking here, the domain of our derivative, we got to check this whole does not exist. And it doesn't matter what x is, whether x is positive, negative, or 0, x squared will be 0 or positive. And when I add 1 to that, the lowest this denominator could ever be is 1. So that denominator is never 0. Similarly over here, no matter what I put in for x, when I subtract 9 and square it, it's going to be 0 or positive. If this is 0, when I add 1 to it, this denominator is always going to be positive as well. So the domain happens to be all real numbers because my denominators are always positive. Interesting. This is monotonic on certain intervals. Interesting. So we don't have to worry about does not exist. So instead we set it equal to 0. And if we set this equal to 0, that's the same as saying 1 over 1 plus x minus 9 all squared equals 1 over 1 plus x squared. right? Because I just add my fraction to the other side. But if the reciprocals are equal, then the functions, the denominators must be equal. But hey, let's subtract 1 from both sides. And we've reduced our derivative being 0 to where x minus 9 squared equals x squared. Remember to FOIL this out. Let's subtract x squared from both sides. When we subtract x from both sides, we'll end up with 81 equals 18x. And 81 is 9 times 9, 18 is 9 times 2. And we'll get 9 halves for our x value. And that was a lot of work to get there, but I stand by it. We did calculus, and then we did algebra, a whole lot of algebra. It's always the algebra. But remember, our y value is always the function evaluated at 9 halves, or 4.5 if you prefer. So this is the arctangent of 4.5 minus the arctangent of 4.5 minus 9. And that's where we pull out a calculator. Oh my goodness, I just happen to have it there. How wild. And this gives us 2 point, I forgot to pay attention, 704, right? We want 3 decimal places. The 4 is the third decimal place, 2 to the right of it, so 704. So the x value we get from where the derivative is equal to 0. So we can find the derivative in arctangent. And once we find the x value, then we plug it into the original to find the y, and that's why we're thankful for calculators. I do not expect you to find the arctangent of 4.5 by mental capacity only. Use a calculator. How are we doing? Fantastic.
Pretty good. Thank you. How are you doing?
I'm all right. I feel like I'm talking a lot though.
No, I appreciate you doing this, really.
Good. All right. Well, this one. You're really going to appreciate this one. I think I have a separate video possibly in my calculus playlist on YouTube that talks about this specific problem. Or maybe I just have it written up. I don't know. But I kind of like it. Let's do it. Also, it's the last problem on the homework, so you know that it's always going to be the challenging one. So instead of making you work for it, I'm just going to talk about it. So I'm going to call this 5. I'm going to put it right here. I'm going to put the x right here. Just, I know it's right there. I know it just because it's easier for me. I'm going to call this distance between the observer and the plane. An airplane flies at an altitude of 5 miles at a point directly over an observer. Consider theta and x is shown in the figure below. Write theta as a function of x. Okay, now as I'm looking at theta, x, and 5, anytime we're talking about angles, we're in trigonometry. This is the opposite, and this is adjacent. So that's all I have. Tangent of theta is opposite over adjacent. But we want theta to be our output and x to be our input. So theta is equal to arctangent of 5x. You could also write tan inverse of 5 over x. Either one. The book frequently uses arctan, and you could just type it. You don't have to find the special function. You could just literally type the letters ARCTAN, and then it'll pop up parentheses for you. The good news Oh, I didn't put it in yet. Let's see if it works. Arctan of 5 over x. Yeah, so we don't have to go to that special find a function button because that's sometimes frustrating. Like I can't find it. Where is it? Okay, so we have our function. Now the speed of the plane is 328 miles per hour. That is going to be our dx dt, right? That's the rate at which the plane is coming towards us. And it will be a negative because the plane is closing distance, all right? So since the plane is coming towards us, it's going to be a negative. If the plane was faced the other direction, this would be a positive because the distance from us would be increasing. Miles per hour. Find d theta dt when x equals 10 and when x equals 5, round to 3 decimal places. Here we go. So we start with theta of x is the arctangent of 5 over x. We're looking for related rates. Taking us all the way back to section 2.6. But we know that d theta dt is, all right, so every time we take a derivative, there's a dt. So the derivative of arctangent is the derivative of the inside, and I'm going to write it like this. That's actually d dt. The derivative of the inside divided by 1 plus the inside squared. All right, so now if we look at 5 over x, let's put this as a side note here. 5 over x is the same as 5x to the negative 1. The derivative is negative 5x to the negative 2. So that's negative 5 over x squared. However, remember x is also a function of time. So that will be times dx dt. All right, this was assuming x is our variable, but we want the variable with, we want the derivative with t as the variable. So we'll have to multiply by that dx dt. But we know what that dx dt is. Oh, man, this is horrible. Okay. Negative 5 over let's do this the right way. Let's put in 10. Negative 5 over 10 squared times negative 328, all divided by 1 plus 25 over 10 squared. And you guessed it right here. Right? We're finished with derivatives. We've done all the calculus. It's all about why did that square not move? It's just algebra and horrible stuff. Negative 5 over 100, that's a negative 0.05, right? Tenths hundredths times negative 328. Make sure that decimal's there. 25 over 100 is a quarter. 1 plus a quarter is 5/4 or 1.25 because I'm pulling out a calculator for this. And we see that both the negative 0.05 and the negative 328, since they're both negative, I know my answer is going to be positive. 0.05 times 328, all divided by 1.25, 13.12 radians per hour. And really, I could write it on there, but that doesn't make it so. It says round your round to 3 decimal places. Fingers crossed. Okay, good news. We did it right. So I'm going to leave the other one for you to do. I don't want to do all the problem. And really, you're starting from there. You don't have to invent the wheel every time you want to go someplace, right? You hop in a car that already has it. So if you're just evaluating a different x equals 5, why do this all over again? You already have it. Just plug in x equals 5 here and go from there. And that is the last problem on the homework. But I was really hoping we would run out of time before we got to this one. But I'm going to work through this one too, for a couple of reasons. Each question is worth 0.2. How much effort am I going to put in this? So let's make sure that the effort you put into it is going to give you at least some points. Here we go. Analyze and sketch the graph of the function. I'm sure there's more down here and I didn't clip it. I don't know. Identify any relative extrema, points of inflection, and asymptotes. Use a graphing utility which you're not allowed to use to verify your results. If an answer does not exist, enter DNE. Okay. Arc cosine. Oh, cofunctions. So the derivative of the arc cosine of u is, because it's a cofunction, it's negative. Because it's the cofunction of sine, it's going to be this. So this is the sine part, and that's the co. The negative sign gives us co, and the rest of it is just the formula for sine. So when we find our derivative here, this is going to be the derivative of the inside. Well, that's not too bad. U equals x over 7. But that's also just 1/7 x. So the derivative of the inside is 1/7, right? It's nice that that variable is in the numerator and not in the denominator. 1 minus x over 7 squared. And I'm definitely going to simplify this. I don't know why I felt the need to write that over there. I was probably going to try to cram something else in there. Okay. X squared over 49. 1 minus x squared over 49. So that's going to be 49 minus x squared all over 49, right? Because 1 is the same as 49 over 49. Subtract them. This is not nearly enough space, but I'm going to write it anyways. Square root of 49 minus x squared all over 7. And that's okay, because this 1/7 and this 7, my 7s, these are going to cancel out. And my derivative becomes 1 over the square root of 49 minus x squared. All right. So it looks like we have some issues when x equals plus or minus 7. So that's an issue. It looks like this domain has to be from -7 to 7 only. Why? 49 minus x squared, we can't have a negative number under the radical to have it a real valued function. So if x squared is anything larger than 49, I'm going to be getting a negative number under here. So if x is anything larger than 7, when I square it, it'll be larger than 49. So I can only be between -7 and 7 for the domain of this function. So that's something to keep an eye on. What else? So this whole does not exist idea is there. Points of inflection too. Oh, okay, I got this. The first derivative is never 0 because the numerator is never 0. If there's no variable in the numerator, that function, that fraction, that rational expression, that's never going to be 0. So minimums, maximums is not going to have one of them, it seems. Points of inflection, we're looking at second derivative. We're going to keep an eye on that. I want to take this question off. That's seriously. Let's bring up Desmos and take a look. All right, well, good news. We could go away here. Oh, I know the controls now. Control Shift Alt H. Okay, good news. Arc cosine really is defined from -7 to 7. Fantastic. It doesn't look like we have any asymptotes here at all, a horizontal or vertical. And it looks to always be decreasing. And there's like no points of inflection. What in the world? I don't like this problem. I don't like it at all. It hurts my head. Yeah, I'm going to say it does not exist, does not exist, does not exist. Let's see how it goes. Let's see. All right, there's no asymptotes. All right, because the original function is, let's make it happen. The original function is defined. From -7 to 7, because we can find the arc cosine of -1. Let me scroll and make sure. Trying to do a slow scroll so I don't like kill your eyes as I do it, but I really just want to get up here. Arc cosine of x, yep, or equal to, because we have x over 7, that extends this to from -7 to 7. So the derivative is never 0 because the numerator is never 0. We see that f at -7. Ah, man, I'm struggling, guys. I know better. I totally know better. Let's find the second derivative. The second derivative is if I write it as 49 minus x squared to the -1/2, I will have bring down the exponent, subtract 1, leave the inside alone, and then multiply by the derivative of the inside. All right, little chain rule going on here. The 2 and the 1/2 cancel out. The negative and the negative are all cool. So I'll get x over 49 minus x squared to the 3/2. Again, the numerator is going to tell us we're at 0. So we will have a point of inflection at 0. Let's see if we can see that in our graph. So this is cupped up, right? This is cupped down. So it had to switch somewhere. I'm going to call it 0 and pi over 2. How handy I didn't have to evaluate that. 0 comma pi over 2 because the y value is the arc cosine of 0 over 7. which is the arc cosine of 0. What makes cosine equal to 0? Pi over 2 does. And look again, my over 2 didn't transfer with me, but the other stuff rolled. I'm guessing my maximums and minimums are at the 7s, and I'm not sure which one's a maximum or which one's a minimum. There's definitely something funky going on at the 7s. So I'm going to use the second derivative test because I haven't really used it in class, because who does? Let's check it out. Let's find f double prime of -7. The second derivative at -7, that's still undefined. Ah! I'm not entirely sure which one. I mean, obviously, according to our graph, -7 comma pi is going to be our biggest value. And 7, 0 will be our minimum. Other than Desmos is awesome, we need to know why and how we would find these. Oh, yeah. Critical numbers, the endpoints are also critical numbers. Just evaluate at the endpoints. At -7, the arc cosine of -7 over 7 is the arc cosine of -1. What makes cosine -1? The cosine graph dips down at pi. And we would evaluate the other endpoint. I was making it too complicated. And I know you guys have never done that before, right? It's so easy to do. So I know that the endpoints also are critical numbers, where the derivative is 0, where the derivative does not exist, and endpoints of a closed interval. And since this is only defined on a closed interval, our endpoints are going to give us our maximum and minimum. So I made that way harder than necessary. Hopefully, in order to make it easier for you guys. All right. How we doing? Is that okay? No, we're still writing it down. That was crazy. We have 15 minutes. Fantastic. Thank you for the feedback. We have 15 minutes. I want to talk about, all right, I'm going to save that. I want to talk about a problem on, what was it? It was 5.2, I believe. Yes, that table function. I was really bummed that yesterday didn't get recorded, specifically because of, it wasn't, what was it, 5.4? The table that we did on Desmos to help out this problem, it was exponential, indeed. Yes, this one. So I want to talk about this one a little bit because the recording didn't happen because let's look at this side by side again. A valve on a storage tank is open. I just want to go through how to set this up on Desmos. What I'm looking for is linear regression capabilities in my graphing utility. But we're looking for points of the form t comma natural log of r. So I'm going to go to the table. So use the plus sign, go to the table. My x1 values are going to be my t values. All right. And my y values will be ln of 424. So I'm taking the natural log of each of these. All right. And so you can see that they all line up really well. They end up being in a line, and the R values themselves, definitely not linear. This is a logarithmic graph. And we can now say we just type y1, and it automatically puts it down as a subscript, a tilde, twiddle, mx1 plus b. And it will give you the equations. So your a value would be your m. Your b value is given here. Make sure you use t, and then you'll translate this. Make both of these the exponent of an exponential function of base e, and you'll be good to go. All right, but that table, just in case you forgot, because it's been a couple of months now since we've done one, that's how you would do that table. The rest of the work, like the actual notes of it, are on the class notes for yesterday, even though I forgot the recording. So the written part of this problem, 5.4, number 12, is there. Now you have the visual for it also. And that, my friends, concludes today's edition of How Can Tuesday Get Confused by Calculus? I hope you've enjoyed the show.